Hello everyone, welcome to my YouTube channel Just to Pull. In this tutorial series, we will be looking into modern C++ concurrency, where we will mostly deal with what is concurrency and how to implement it using modern C++. So let's get started. In this introduction, we will be mostly looking into what are the preliminaries for the concurrency. We'll check what exactly is the concurrency. Should we really use it in our application? Then we'll see few fundamental rules behind designing a multi-threaded applications. Then we'll code our first program using a multi-threaded architecture or a C++ standard thread library. I would recommend you to read Concurrency with Modern C++ by Rainer Green. And the another book is Concurrency in Action by Anthony Williams. This is my personal favorite. I would recommend you to read this. We will see a modern computer architecture. So all modern day computer are based on von Neumann architecture. Again, I mean, some people may disagree and say most modern day computers use Harvard architectures. Well, both statements are true. It is just an opinion, and in fact both are again true. It depends on your computer system. If you want to know more about what is Harvard architecture, what is von Neumann architecture, please feel free to check out the Wikipedia page. So in terms of von Neumann architecture, so there is a input, basically few instructions. Then those instructions goes into memory. From memory there is a to and fro action. From memory it goes to control unit and logic unit. So this collectively it's called as a CPU. And yeah, the to and fro operations happen in between memory and a CPU, and at the end we'll get some output based on our instructions. So in terms of processors, so this could be very well your Intel Core i9 processor with maybe 16 cores or 4 cores. It could be anything, or any processor for that matter. Well, there used to be a single core machine, but that era is long gone when computer used to have only one core. So all modern day computers and processors may have something similar like this structure. So this is a chipset. Over chipset you could have multiple cores aligned, maybe in this fashion or any other, but yeah, the overall architecture remains the same. So what is the core then? So a core or a CPU core is nothing but brain of your computer. It receives some instructions from user and executes those instructions. Core consists of registers, an ALU, a control unit, and a cache. So what is thread then? A thread is nothing but a sequence of instructions which can be handled independently by your OS scheduler. Almost all modern processors are multi-core processors now. I mean, look at your PC. It is also a multi-core processor. We need to check few other facts such as what is homogeneous system, what is heterogeneous system. So homogeneous system means a processor that has all cores identical, like all of them are identical. And heterogeneous system means there are more than one types of cores are being used on a specific chipset. I believe most computer systems are nowadays are heterogeneous, but yeah, I mean, again, this is just an opinion and it could vary from system to system. Feel free to check out these terminologies, homogeneous system and heterogeneous system. Like for example, in terms of CUDA computing, it is always a heterogeneous system. It really matters which system we are using. Most of the time these like few tweaks are done for performance and efficiency gains. There is no significance as such. There are few facts. On a computer system there are two types of memories. One is a main memory, another is a cache memory. So we'll see a cache memory first. A cache is nothing but a memory which is on your core. It is the fastest memory used to store a data and copies of your instructions. So if you remember the diagram that we shown earlier, on one specific core there is additional cache memory within that core. So the component of a system that stores program instructions and data is a main memory, and it is very slow compared to the core speed and a cache memory. On a hardware level, instruction cache and a data cache may or may not be separate, or it may be combined. Well, whenever we buy a computer, we must check this L1 cache. So L1 is a core specific cache memory. That means it is on core on chip memory. All other higher memories are being shared by all the cores. Say suppose you have 4 cores on your machine. So for number 1, number 2, number 3, number 4, for each individual core there is a L1 cache for it, and L2, L3, L4 or n number of caches all are being shared by all these 4. So what is concurrency? Concurrency is an abstract situation where multiple threads execute over a certain time period where no threads runs simultaneously. That means it is just letting us believe that we are running all the operations in a concurrent way, but it is not. So how this happens? This happens with the use of context switching. Context switching is a technique where CPU time is shared across all the running processes, and it is a key for multitasking. It's collection of a data about your process which allows processes to either suspend or hold information to resume the execution or kill the process. When we talk about parallelism, parallelism is all about performance, whereas concurrency is all about switching between existing tasks. There are two primary classifications of a parallelism: task parallelism and a data parallelism. Task parallelism is nothing but dividing existing tasks into multiple parts and run them in a parallel for better performance. For example, we as a software developers, we do this in our daily life. So suppose you want to develop an application, we divide tasks like developers will write some code and build the application. QA will run some quality tests, and support professionals will take some feedback from the customers. So the tasks are being broken such that those can be run in parallel. In terms of data parallelism nothing but each thread performs same operation on a different part of the same data, focuses on distributing the data across multiple cores. Again, there is a data partitioning which is important aspect. Data partitioning is like there are two basic approaches of data partitioning. One is blockwise and other is cycle-wise. Each thread takes one portion of a data, usually an equal portion of a data. So suppose you have like 1 gigabytes of text file. We break the text file such that, for example, you have a 4 cores. Break it such that each portion is equal. So that is a blockwise data partitioning. There is another data partitioning called cyclic data partitioning, where each thread takes more than one portion of a data. These are few important aspects, and we'll over the period we'll look into it and we'll grab some in-depth knowledge about it. So what exactly is a context switching? So in a multi-threaded process on a single processor, the processor can switch execution resources between threads, resulting in a concurrent execution. In the same multi-threaded process, in a shared memory multiprocessors environment, each thread in the process can run on separate processor at the same time, resulting in parallel execution. So in order to explain this, say we have number of tasks, but we have only one core. We want to run all the tasks on that particular core. So what we'll do, we'll take a task. Core basically performs certain types of actions. It performs a task 1 up to certain limit, say for example 50%. Then it, like, for a moment it pauses the task 1 and moves to task 2. Then it performs certain amount of task 2. Again it pauses the task 2 and moves to task 3. Again it does some certain amount of task about a task 3, and then it moves on to task 1 again, and we resume it. So we store the data related to processes in order to either pause it, resume the task, or kill the process, right? So imagine you are watching a movie and you find it interesting, but suddenly you get a call from someone. Then what do? Of course, you pause the movie, attend the call, and then again continue watching the movie. So this is how context switching works. So computers behave no differently. Note that there is a slight delay in action which may not be visible, but yeah, it is still there. Should I really use multi-threading for my application? We should fully utilize all cores for maybe your simulation applications or computer graphics applications, your user interfaces for specific applications. Improving the application responsiveness, we must use multi-threading. Nobody likes not responding application status. Simplifying tasks in hand, we should go for multi-threading. If tasks are real independent, then go for multi-threading. But again, remember, with great power comes great responsibility. There are some design rules. Identify independent tasks. Use multi-threading only with independent tasks. Otherwise, we'll run into racing situations. What do we mean by racing situations? Suppose there is thread A and thread B, and thread A requires some information from thread B, and thread B requires some information from thread A. Now they run into situation where thread A is waiting for thread B to provide some input, but thread B is waiting for thread A to provide some input. That means both are now stuck and they are not going to perform the task. So this is a racing situation. So we should avoid that. We must make all the tasks as independent as possible. And if those are independent, then only go for multi-threading. Check if you really need it. You don't need a car to drive just to go across the road, right? I mean, it will in fact take more time, like for example taking out your car from your garage and then make a turn and cross the road by of course looking at traffic signals, right? Where you can just simply walk across the road, uh, which is quite faster than a multi-threading. Number of cores soon will increase. Write a code such that it will take care of future changes and adapt your coding. Make it scalable, and if possible use implicit libraries like threading building block from Intel. Explicit library may not give you a finer control, but yeah, again using libraries like Intel TBB may help. Now let's write a simple code for our first multi-threading application. We should include all necessary libraries first. C++11 thread library, which provides us the thread object to use. Now, so in order to manage the threads, there are multiple ways to invoke a thread, but we'll just simply look a function pointer or a function, a simple function. Let's write a code let's write a function for a hello concurrency world, and then we'll write right. So just for identification, I'm writing from thread kernel, so which will let us know this is from a thread. Then I'll just create a thread object, my thread, and then I'll call function hello concurrency world over here. Once we create a thread, we must join it. We'll see in detail about all join, detach operations, how thread can be managed, everything in detail from the next tutorial onwards. So for the time being, let's just check if this code works. Indeed it does, but I'm not sure whether this is the correct multi-threaded application or the multi-threaded kernel that we called. So just for the verification, let's write some more code into this. So with standard this thread, we can get ID for this particular thread. Let's say slash. Alright. So this will give us the thread ID for a particular thread, or in this case my thread. Now in main, let's write some piece of a code. I'll just copy this portion, paste it over here, and yeah, and this one is from main. So let's now check it. So if you can see, the hello concurrency word from a thread kernel gives some value, and hello concurrency word from main gives some other value, and these two values are different. That means from main we are invoking another thread, and on that thread we are calling this function. Of course, just for printing hello world, this is not a wise application to create, but since we are getting started, we'll just anyway do it. Okay, in terms of these values, these are not always being same. For each time you compile and run the program, these values are going to be different every time you run it. But that's not the point. The point here is your main function value and your kernel function value has to be different. Then and then only you can say that my hello concurrency world from a thread kernel is being run on this particular thread. Alright, that's it for this first video. We'll see you soon. Thank you.